This lesson's about potential dividers, and here are your objectives. So here's a simple series circuit. Let's say that this is a 9-volt cell, and we're going to call that V in. It's the potential difference being supplied to the circuit. Let's say this is resistor 1, and this is resistor 2, and resistor 1 has a 1 ohm resistance, and resistor 2 has a 2 ohm resistance. We know that we're going to see a 3-volt potential drop here at resistor 1, and a 6-volt potential drop here at resistor 2, because in series circuits like this, the resistors divide the potential in ratio to their resistances. So a circuit like this is called a potential divider circuit because of that fact, because the resistors are going to divide the potential from the cell in ratio to their resistances. Here we saw a 1 to 2 ratio of the resistances, and therefore a 1 to 2 ratio of the potential dropped at each resistor. If they were both 1 ohm resistors, then we would have seen a 4.5 volt potential drop at each. So this is called a potential divider circuit, and in general, if we were to connect leads here, so I'm going to connect a lead here, and I'm going to connect a lead here, and across here I could either put a voltmeter, or I could put a lamp, or some other kind of load. We're going to call the potential difference observed here V out. So V out is in parallel to resistor 2. And by this same reasoning, V out is going to be equal to V in, which in our example was 9 volts, multiplied by R2 divided by R1 plus R2. So in our example, R2 was 2 ohms, R1 was 1 ohm, and R2 was 2 ohms. So we got 2 over 3 here, and 2/3 of 9 volts was the 6 volts that we measured. So this is just a more general expression for the potential difference that we could measure here across this resistor as a function of the cell and the resistances of the two resistor. This is called the potential divider equation. Now, this kind of thing allows us to basically create an on-off dimmer switch for circuits. Let's step back a moment and think about ways that we could control the power to a load. Here is one way. This symbol here is a variable resistor. That's what the arrow means, and this is our bulb or our lamp. And if we increase the resistance of this variable resistor, it's going to decrease the current overall, because remember that the potential difference supplied by the cell is equal to the total current out of the cell multiplied by the equivalent resistance of the whole circuit. If I increase the equivalent resistance of the whole circuit and the cell doesn't change, then I must be decreasing the current. So increasing this resistance is going to decrease the current, and also by the reasoning that we showed above, increasing the resistance of this resistor is going to increase the potential drop across this resistor as a fraction of the whole thing. More of V in is going to be dropped over here, and therefore I've got both lower current to this bulb and I've got less potential drop over here as well. Remember that power is equal to the current through a load multiplied by the potential difference across it, and so if both of these are decreasing, the power will decrease as well. Power is what we would observe as brightness in the lamp, and therefore this would form a way of dimming this lamp. So here's that circuit in the PhET simulation. Here's the URL at the top. We've got the current and the voltage being measured, and if I were to change this resistance, first I can drop the resistance. Notice that we see the current go up, and we also saw the share of the cell's potential difference that's being dropped at the lamp go up. And now if I increase the resistance, we see the current coming down and the share of the voltage that's at the bulb going down as well. Notice that the bulb is getting dimmer. Also notice that we can get all the way up here, and even though we have a large resistance here, we still see a little bit of light. So we haven't been able to switch the light completely off because there still is both a current and a potential difference here at this lamp, and therefore we still see power evidenced as the brightness. So we actually haven't been able to switch it completely off. This is a variable resistor, also called a rheostat, when we can change this up and down. And so connecting it in series with this bulb has given us one way of dimming the bulb, but not switching it entirely off. Here's another setup called a variable potential divider, or a potentiometer, that offers some advantages. So imagine that both of these now are variable resistors, and we'll call this resistance 1 and this is resistance 2, and now we have a bulb, a lamp, connected in parallel with resistance 2. So this is going to be our V out, like we saw in the initial example. Well, remember that V out is equal to V in, that's down here, V in, multiplied by the ratio of R2 to the total resistance R1 plus R2. What that's telling us is that if I were to increase resistance 2 and decrease resistance 1, then V out would get bigger because I'm increasing this and I'm decreasing this. So bigger fraction of the resistance resides here at resistance 2. In contrast, if I were to decrease resistance 2 and increase resistance 1, then V out would decrease. So I have a way of controlling the potential difference supplied to the bulb by controlling the relative resistances of the two resistors. Let's look at that in a simulation. I've got two variable resistors and a bulb connected in parallel with a second. Notice that if I drop the resistance of this to make it effectively a wire, then now I have the full 20 volt potential difference supplied by the cell being dropped across the bulb, and the bulb is bright. In contrast, if I put this back up, let's say to 10 ohms, and now I drop this one and make this into a wire with zero resistance, now I have zero potential difference across the bulb, and notice that now the bulb is completely out. There's no current through it, there's no potential difference across it, so by power is equal to current times potential difference, I have zero power being delivered to the bulb, and the bulb is completely off, not like what we saw in the previous setup. So how do you set that up practically? Well, one way of doing it is to take a resistor that consists of a coil of wire and to have a lead coming in, a lead coming out, and a third lead that slides up and down, backwards and forwards, that changes how much of this length is in parallel with the bulb and how much is in series. So remember that for wires, the resistance is proportional to the length. So let's think of this as a wire. The portion on the right over here is in parallel with the bulb, and that is resistor 2. So in green here, that's resistor 2. Whereas this portion over here in red is like resistor 1, and that's in series with this parallel connection of the bulb and resistor 2. So that's resistor 1. And as I slide to the right, I decrease the length and therefore drop the resistance of resistor 2 in parallel, and increase the length and therefore increase the resistance of resistor 1 that's in series, and vice versa if I move to the left. So by sliding this up and down, I am controlling the resistances of these two resistors. We've taken this setup and we've operationalized it like this. Also notice that we can move that slider to one side entirely. So if this is a 9 volt cell, here we would see a total of 0 volts across the bulb and 9 volts across this resistor. And we could also move it to the other side, where now if this is a 9 volt cell, we would see 9 volts across each of these because they're both connected in parallel. This is the situation where the bulb was off, and this is the situation where the bulb was as bright as we could get it. So this variable potential divider setup allows us another way of controlling the power to the bulb. And in contrast to the variable resistor in series that we saw here, the potentiometer, or the variable potential divider, has the advantage that it allows us to get down to a potential difference of 0 across the load, and therefore switch, in our example, the lamp completely off. So that's variable potential dividers.